So in this video we are going to see this problem. Okay, 100 meter square of solar panel is coupled to a flywheel such that it converts the incident sunlight into mechanical energy of rotation with a 1% efficiency. Okay, with what angular velocity would a solid cylindrical flywheel of mass 500 kg and radius 50 centimeter be rotating if it starts from rest at the end of 8 hours of exposure of a solar panel? Okay, and take the solar constant to be 2 calories per centimeter square per minute for the full time interval, and 1 calorie is given as 4.2 joules. Okay, so suppose the flywheel whose axle is horizontal were suddenly released from its stationary bearings and allowed to start rolling along the horizontal surface with a coefficient of kinetic friction mu is equal to 0.1. How far will it roll before it stops slipping? Okay, with what speed is the center of mass moving at that moment? And the last one, how much energy was dissipated as heat? Okay, so we are given a flywheel, okay, which is connected to a solar panel, and the area of the flywheel is 100 meter square. Okay, and the sunlight is falling onto the solar panel, and so it is converting electrical energy into mechanical energy, and with 1% of efficiency. And with what angular velocity would the solid cylindrical flywheel of mass of the flywheel is given as 500 kg and radius is 50 centimeter, will be rotating at the end of 8 hours of exposure? So we are giving 8 hours of exposure, and what is the angular speed at the end of 8 hours? And the solar constant, as you know, what is solar constant? It is the amount of radiation which is falling per unit area per unit time normal to any given surface, right? That is solar constant. And suppose the amount of solar energy which is falling normal to the surface per unit area per unit time, that is called a solar constant. And the for the entire time interval, the solar constant is given to you as 2 calories per centimeter square per minute, and as we know, 1 calorie is equal to 4.2 joules. Suppose the flywheel whose axle is horizontal with the axle is horizontal was suddenly released. So the axle of the flywheel is released, okay, and from the stationary bearings, and allowed to start rolling. Okay, it is allowed to start rolling along horizontal surface, and the coefficient of kinetic friction of that surface is 0.1. So how far will it roll before it stops slipping? Okay, so you know that when friction is acting, there is a slipping on the of the flywheel. The flywheel will slip on the floor. With what speed is the center of mass moving at that moment? At which moment? At the moment when it stops slipping. Okay, what is the speed of the center of mass? How much energy was dissipated as heat? Okay, how much energy was dissipated as heat? That is what is asked here. So to approach this problem, okay, let us first take the rotational kinetic energy. As we know, the rotational kinetic energy, let me call it as E, okay, and that you know is equal to half into I into omega square, isn't it? Where I is what? I is the moment of inertia. So moment of inertia of a cylinder, okay, moment of inertia of a cylinder is how much? I is equal to mr square divided by 2. Okay, so you can write omega as how can you write omega? Omega is equal to this, I can write as omega 0 square, because let omega 0 be the initial the velocity, the velocity of the what after 8 hours of rotation. Let us say the omega be the angular velocity attained by the wheel. Okay, so the angular velocity of the wheel is omega naught. So omega naught can be written as here 2e divided by I. I is the moment of inertia and its root, isn't it? So this is the energy. Now, what is the energy here? How much is the energy? So in order to calculate energy, it is given that the area and a solar constant is given to you as how much? 2 calorie. 2 calorie means 2 into 4.2. Okay, 2 into 4.2. That is 1 calorie is 4.2 joules per centimeter square. Okay, so per centimeter square means into 10 to the power 4 meter square into area. So this is the area into, and its area is 10 to the power 4. We convert into centimeter square to meter square, so into 10 to the power 4 into 100. 100 is the area. So the solar constant is given as a 2 calorie per centimeter square per minute. So per centimeter square you convert into meter square, so it will become, you have to multiply with 10 power 4, and then you have the area of the cylinder given as a cross section of the cylinder is 100 meter square. Okay, and into time. What's the time? Time is 8 hours. Okay, so 8 hours means 8 into 60 minutes, isn't it? 8 into 60. This is the energy, and it is converting only 1%. 1% means 0.01, right? 0.01. So this is the energy which you will get, right? And what is moment of inertia? Moment of inertia is half into m, mass. What is the mass given to you? Mass is given to you as 500 kg. So half into 500 into r square, radius. What is the radius? Radius is given to you as 50 centimeter. 50 centimeter is 0.5 meter whole square. So you know E, you know I. Okay, so now you can find what is omega naught. So this omega naught here, omega naught value comes out to be 1136 radians per second. Okay, so this is the value of omega naught which we get. So the omega naught comes out to be 1136 radians per second. Okay, right. Now let us consider a horizontal surface. Okay, horizontal surface, and this is our flywheel. So this is our flywheel, and this flywheel is now rotating about its axis with an angular velocity omega, right? So it is rotating with an angular velocity omega. So since it is rotating at this moment, at this point, the velocity is this direction, so that means the friction will be in this direction. Friction will be in opposite direction, isn't it? Friction will be in the opposite direction. So now if we consider the equation of motion, okay, equation of motion. So when the wheel is rotating and it is attaining a final velocity of omega naught, right? After 8 hours it is. So let us calculate the equation of motion. So equation of motion is what? It is the torque which is acting, which is equal to the torque. Okay, torque is given by I into alpha, right? And which is equal to minus force into perpendicular distance. So force into perpendicular distance is the radius, isn't it? So force is the frictional force, and so here this torque on the, so friction produces an opposite torque, isn't it? So torque due to friction is opposite to that of the rotation, the actual torque of the rotation of the flywheel. So in whatever direction the flywheel is rotating, the friction will produce an anti-torque, right? So that is equal to minus F into R, right? And this I into alpha you can also write as I into d omega by dt. All right. So this is the rotational force, rotational torque you are calculating. Now if you calculate the force which is acting, okay, force which is acting on this flywheel, force F, you can write force F as how much force is nothing but your force which is making the body to move forward is your frictional force, isn't it? So you can write force small f is equal to m into a, right, which is equal to m into dv by dt. So this is the frictional force, is the force which is acting on it. This is the only force which is acting on this flywheel, which is equal to m into a, right? So which is the acceleration on the acceleration on this flywheel is only because of the friction, isn't it? So this is the friction, force of friction. So force of friction is given by m into a, which is equal to dv by dt. Okay, now if you take the boundary conditions, what are the boundary conditions? So the boundary conditions, if you take the boundary conditions, okay, so at omega is equal to omega 0, at omega is equal to omega 0, your velocity is equal to 0, isn't it? That the body is just having a rotational motion, it is not having any translational motion. So velocity is equal to 0, and that is at time t equal to 0, at the beginning, at the initially, right? And when omega is equal to omega 1, that is when it stops slipping, okay? At that time the velocity is equal to v1, which is equal to r omega 1, okay? And at that time the time is equal to t is equal to t1. All right, so these are the boundary conditions. This is the boundary condition which we have for this particular flywheel, the motion of this flywheel, okay? Now here so omega 1 is the velocity. So what is omega 1? Omega 1 is the velocity, that means the angular velocity, right? So the angular velocity at the instant the flywheel stops slipping, isn't it? So it is the angular velocity at the moment when it stops slipping. Now here we are going to calculate what let us see the equations of motion once again. So what are the equations of motion that we have got? The equations of motion are I into alpha, right? So I into alpha, that is equal to I into d omega by dt, right? I into alpha, which is equal to I into d omega by dt, which is equal to minus f into r. Now cross multiplying, I will get I into d omega is equal to minus fr into dt, right? So when you integrate it, so you will get, on integrating, you will get integral I into d omega is equal to integral minus fr into dt, right? This is from omega naught to omega 1, and this is from 0 to t1, okay, t1. This is the so when you integrate it, you will get the relation, you will get something like this. The relation which you will get is I into, so this gives you I into omega 1 minus omega 0, okay, that is equal to minus fr into t1, okay? So this is the nothing but the rotational impulse, is equal to rotational impulse, okay? which is equal to the change in angular momentum. Change in angular momentum, right? Change in angular momentum. So here the rotational impulse is equal to change in angular momentum, right? So this equation you are getting I into omega 1 minus omega 0 is equal to F into R into T1, right? So that means the rotational impulse is equal to the change in angular momentum. In that way also we can arrive at this relation, right? Now if you consider the second equation, that is m into a. So F is equal to m into a. F is equal to the frictional force, F is equal to m into a. That is equal to m into dv by dt, right? So you will get the relation m into, which will give you m into v1, which is equal to F into t1, right? Or you will get m into r omega 1 is equal to F into t1. Okay, so this is the second equation you are getting. So our first equation is what? The first equation is I into omega minus omega 1 minus omega 0, okay, that is equal to minus F R T1, right? And second equation you are getting m into r into omega 1 is equal to F into T1. And you know I, what is moment of inertia? That is equal to mr square divided by 2. So if you substitute that value here and solve it, okay, so if you divide these two equations, okay, solving this, you will get solving these two equations, okay, solving these two equations, that is, this is equation number 1 and this is equation number 2. So solving these two equations, solving 1 and 2, we get, solving 1 and 2, we get omega 1 is equal to omega 0 divided by 3. Okay, so omega 1 is equal to omega 0 divided by 3. Okay, so this is what is the omega, the final angular velocity when it stops slipping, right? So before that, what is the distance traveled? So distance traveled is given by ut plus half at square, right? So s is equal to, your initial velocity is 0 plus half into a into t square. This is the distance traveled. So that is equal to half into acceleration is force by mass, F by m into t square, right? So you got the angular velocity. Now we are calculating the distance traveled, right? So half into F by m. And what is F? F is the frictional force, which is equal to mu into the normal reaction, which is the weight. So frictional force is F is equal to mu m. And what is T? Time. So in order to calculate time, how will you calculate time? So for that you have the formula. So how will you calculate time? So let us calculate here. That is mr omega 1, right? That is equal to F into T1. So we can calculate from here. Omega 1 is equal to omega 0 by 3, right? So on calculating this, and F is equal to mu mg. So on calculating this, you will get T1 is equal to r omega 0 divided by 3 mu g. Okay, so this is the T1 value, what you are getting, T1 value. Okay, so the time you are getting as r omega 0 divided by 3 mu g, which we are getting from calculating the force. So force, so calculating the force, on calculating the force and then integrating it, you are getting this relation mr omega 1 is equal to ft1. So using that we can get the time. So this time you can calculate into t1 square. It is actually t1 square. So f is equal to, so using t1 is equal to r omega 0 divided by 3 mu g. Okay, using these two relation, you can calculate the s you will get as omega 0 into r whole square divided by 18 into mu into g. Okay, and what is omega 0? We have already calculated what is the value of omega 0, isn't it? Omega 0 you got as 1136 radians per second. Omega 0 is equal to 1136 radians per second, right? And the radius you know is 0.5 meter, so radius is 0.5 meter, and the mu value the coefficient of friction is 0.1, isn't it? Mu is equal to 0.1, so mu value is equal to 0.1. So calculating all this, you will get the s value. What is the s value we will calculate? So s comes out to be, so this is the equation for calculating s. Okay, so knowing all these value omega 0, r and mu, just you can calculate and you will get the s value. So the s value comes out to be 18,290 meter. So this is the distance traveled before it stops slipping. Okay, before the ball stops, before the flywheel stops slipping, this is the distance traveled. Okay, now let us calculate at any instant, any time which is between the time it stops slipping and before it gets released from the axle. Okay, so this if you calculate, so your equation of motion which you got I into omega minus omega 0 is equal to minus FRT, and the linear motion mv is equal to F into T. So this is what you get on integrating the rotational torque and the linear force when you so this is the linear impulse and the rotational impulse. If you calculate the linear impulse and the rotational impulses, these are the impulses. So this is rotational impulse, rotational and linear impulses. These are the rotational and the linear impulses. Okay, so these are the impulses which you get. Now here what we can do is so velocity mv is equal to ft, you know this. So can I write velocity as ft by m? Yes, I can write ft by m. So your equation is I into omega minus omega 0 is equal to minus FRT. Okay, so I'm going to equate this here. Instead of m, I can write mr square divided by 2 omega minus omega 0 is equal to minus FRT, isn't it? So this if you solve, you will get r omega 0 minus r omega is equal to, you will get 2ft by m. Okay, so this is the equation which you will get. R omega 0 minus r omega is equal to ft by 2ft by m, right? So now also you have the equation that is v is equal to ft by m. Also you have v is equal to ft by m, right? So using this equation and this equation, you will get finally, you will get, what is that? You will get v minus r omega, right? This is the effective velocity at the point of contact. See, this is the point of contact here at this point. This velocity v. Okay, so here there is two velocities it is having, right? So two velocities are there. So actually this point should be at rest. This point should be at rest here. But now it is having an effective velocity v minus r omega, right? That comes out to be 3ft by m minus r into omega 0, right? So this is what is the effective velocity. You can, in other words, you can say this is the effective velocity. V slipping, velocity of slipping, you can say. Velocity of slipping. Velocity of slipping is that is equal to V minus R omega is equal to 3ft by m minus R into omega 0, right? So now we can calculate here what is the formula for power. Okay, so power dissipated by friction. So power dissipated by friction. So what is the power dissipated by friction? How will you calculate the power dissipated by friction? So power, as you know, is given by rate of doing work, isn't it? Power is equal to rate of doing work. So power, so I'm going to calculate power dissipated by friction. So this is the power dissipated by friction. Power dissipated by friction, and power is equal to dW by dt, and this work done is converted as heat, so I can write dQ by dt, isn't it? Power dissipated is equal to dQ by dt. So I can write here dQ by dt, isn't it? So, and power is given as so here you can see that the frictional forces here F, and your V minus velocity V minus R omega is this is this direction. So they both are in opposite direction. So the power dissipated will be equal to, power is equal to F dot V, F dot V minus R omega vector, right? So that means power is equal to minus F into V minus R omega. So this is the power dissipated, which is equal to dQ by dt, the heat generated, right? So dQ can be written as minus F V minus R omega into dt, right? Minus F V minus R omega into dt. So the Q value will be equal to minus integral F into V minus R omega into dt. This is the heat dissipated, okay, the heat dissipated. So to calculate the heat dissipated, so the total heat dissipated is equal to minus V minus R omega, that is V minus R omega you got as 3ft V minus R omega is equal to 3ft by m minus R omega naught, you know that. So I can write minus integral 3ft minus R omega naught, 3ft by m minus R omega naught into f dt. Okay, this you are integrating from where? 0 to t1, because t1 is the time until it slips. That means that at t1 it stops slipping. So t1 is the time when it stops slipping. So this heat generated will come out to be minus 3 h square t1 square divided by 2m plus R omega naught f into t1, right? So this is the heat generated you will get. Now here F value is equal to mu mg, okay, and t1 value is equal to omega naught R divided by 3 mu g, okay. So t1 value you have and f value you have. By calculating these you will get q as how much? M omega naught square into R square divided by 6, okay. So this value if you substitute for mass is given as a mass. If you calculate for mass and then omega naught, so 100 kg, isn't it? 100 kg and omega naught. So all these values you are substituting, mass and omega naught and R. When you substitute, you will get Q as 2.688 into 10 to the power 7 joules. Okay, so this is the amount of heat which is dissipated during the time of it slips. Okay, now this can also be calculated. You can also calculate this in other words, other way. That is, the heat generated is equal to its initial rotational kinetic energy, that is half I omega naught square, minus the final energy when it is that is the total energy, final energy, initial energy minus final energy, that is half I into omega 1 square plus half into m v1 square. Okay, and so by solving these values here, mi is equal to mr square by 2. Okay, and omega 1 is equal to omega naught by 3. Okay, and what is v1? v1 is equal to r omega 1, which is equal to r into omega naught by 3. So just substituting this, you will again get q is equal to m r square omega naught square by 6. So the same value, you are getting the same value which you got previously. So the same value you are getting here. Okay, so the same value which you got previously, that you are getting here, 2.688 into 10 power 7 joules. Okay, so here also you will get the same value, 2.688 into 10 power 7 joules. Right, so this is the value of heat which is dissipated here. Right, so the amount of heat dissipated is equal to 2.688 into 10 to the power 7 joules. Right, so this, in the two ways we can do here. Okay, by calculating the power and then by integrating to find the heat generated, you can calculate, or you can find the initial energy minus the final energy. So that will give you the final energy will be less than the initial energy. So final energy will be the rotational kinetic energy plus the translational kinetic energy. So which difference of which will give you the heat, which is the energy which is lost, and this energy lost is converted into heat. Right, thank you.